Hello, everyone. Today we're going to be going over statistical methods for rates and proportions, Chapter 2, Section 2.3. And in this section, it talks about using the F distribution to create confidence intervals. So we're in the same scenario where we have X following a binomial distribution with a fixed number of trials N and a probability of success P. So we have a few different options that we can use, and hopefully we're going to learn some R as we go along. So we're going to mimic what was in the book and set our observed number of successes to be 23, our number of trials to be 25, and our alpha level to be 0.05. So what we can do is we can calculate our F value by using the QF function. Now, so far, we've learned things like P binom and D binom. And now we're using the F distribution, so we're using QF, but there's also PF and DF as well. But when we have QF, that says if you give me an alpha level and the degrees of freedom associated with that alpha level, then I will tell you the value of F. So this is similar to using tables, but I find it to be a bit easier in R because I don't have to flip through and estimate degrees of freedom, and the computer will do it for me. So I'm also going to tell R lower dot tail equals false, because in our book, it says that alpha relates to the upper tail of the distribution, and we want to match that. So the F value we get by using the QF function is 2.30. All right, and in our book, we can find the lower PL by using the formula in equation 2.8, right? So we've hard-coded that equation, and we get the same exact value of the 0.76 that the book got, or 0.77 if you round. All right. One thing that I notice is that this is a lot of input. I'm setting these values in advance anyways, and then running the code. I could create a function for PL and PU. Okay, so my function is going to have certain inputs. So I'm going to input our x0, the n, and the alpha level, right? And in this function, I have the curly brackets, right? I'm going to calculate the F value that I did before, and then I'm going to have the function output the lower bound. All right, so once I run this function, then nothing gets outputted because it's just telling R what PL the function does. So it's not a built-in function in R, I'm building the function. All right, but here now I can just say, okay, calculate PL, which I just defined, for x0 being 23, n is 25, and alpha being 0.05. So once I've put this function in, I can change any of these values of x0, n, and alpha, and it'll calculate the lower bound very quickly, quicker than I could ever do with a calculator. But in a sense, R is just a giant calculator, right? So here, I get the same exact thing as what I got before, which we used the same notation, we used the same values, so we're happy that we know we coded it correctly. Sometimes I just use that as a check for myself to make sure I didn't make a typo. All right, similar to the equation 2.9 in our book, we could calculate the upper bound for the proportion, right? This is the upper limit of the lower one-sided 100 times 1 minus alpha % confidence interval for P. All right, in the book, right, we see that we have a different equation for this one-sided confidence interval, but by hard coding this into a function, we can get the upper bound. And in our book, there's an example of when we observed 19 successes out of the 25 to get the one-sided confidence interval. So we're going to calculate PU, right? And that upper bound is 0.8899. All right. Now for some trickiness. We could create a function, right, that I just need to tell it x0 and alpha and the type of alternative hypothesis. And from there, I could calculate the confidence interval based on what the alternative hypothesis is. So if the alternative is a greater than test, really my confidence interval is going to be from this lower limit up to 1, right? And if I have a one-sided confidence interval that's a less than, right, my confidence interval is going to go from 0 to that upper limit. And if I have a two-sided confidence interval, then my limits are going to be PL and PU. And at the end of the day, I just want my function to tell me the confidence interval. So I've made a little bit more complicated of a function that is saying my confidence interval is dependent on whether or not I have a one-sided confidence interval or a two-sided confidence interval. And in fact, it makes a difference if this is a less than test or a greater than test. So I'm going to account for all of those things using these if statements. So I can run in this code. And now CI is a function available to me, which I made, which is really nice because we have the examples where we saw 23 successes out of 25, and we want to get a one-sided confidence interval using a greater than test. Here we go. There's our interval, 0.76896 up to 1, right? If we wanted the two-sided interval, we can get it just by running the code right away. And similarly, we could do this for the second example with 19, where we have a less than confidence interval, right? From 0 up to 0.8899. And then we can do a two-sided confidence interval, 0.5487 up to 0.9064. So if you think about this, really, once you write your functions, now it's just a matter of knowing what situation you're looking at, right? So the hardest part is reading the question, identifying your distribution, identifying what is appropriate to use, right? We have a binomial distribution. In this case, we're using the F distribution to get the confidence intervals. And then you just run your code and it does it for you. I hope you learned something today and that you have a great day.